Okay, girls, I am on section 1.2, thermal energy transfers. So this is the beginning. And here are our essential questions. What is the effect of having a small specific heat? What happens to a material when it is heated? In what ways can thermal energy be transferred? And here are the vocabulary words. All right, I am on the red header, how is thermal energy transferred? And this is page 16. Okay, how is thermal energy transferred? Have you ever gotten into a car, such as the one in figure 6, on a hot summer day? You can guess that the inside of the car is hot, even before you touch the door handle. You open the door and hot air seems to pour out of the car. When you touch the material, the metal safety belt buckle, it is hot. How is thermal energy transferred between objects? Thermal energy is transferred in 3 ways: by radiation, conduction, and convection. Radiation. The transfer of thermal energy from one material to another by electromagnetic waves is called radiation. All matter, including the sun, fire, and you, and even ice, transfers thermal energy by radiation. Warm objects emit means give off, more radiation than cold objects do. For example, when you place your hands near a fire, you can more easily feel the transfer of thermal energy by radiation than when you place your hands near a block of ice. Thermal energy from the sun heats the inside of the car in figure 6 by radiation. In fact, radiation is the only way thermal energy can travel from the sun to the earth. This is because space is a vacuum. However, radiation also transfers thermal energy through solids, liquids, and gases. And the word vacuum means, in science, a space that contains little or no matter, but common use, a device for cleaning carpets, rugs, and that uses suction. But we mean this one. All right, next page. Red header, conduction. Suppose it's a hot day and you have a cold glass of lemonade, such as the one in figure 7. The lemonade has a lower temperature than the surrounding air. Therefore, the particles that make up the lemonade have less kinetic energy than the particles that make up the air. When particles with different kinetic energies collide, the particles with higher kinetic energy transfer energy to particles with lower kinetic energy. In figure 7, the particles that make up the air collide with and transfer kinetic energy to the particles that make up the lemonade. As a result, the average kinetic energy or temperature of the particles that make up the lemonade increases. Since kinetic energy is being transferred, thermal energy is being transferred. The transfer of thermal energy between materials by the collisions of particles is called conduction. Conduction continues until the thermal energy of all particles in contact is equal. Thermal conductors and insulators. On a hot day, why does a metal safety buckle in a car feel hotter than the safety belt? Both the buckle and the safety belt receive the same amount of thermal energy from the sun. The metal that makes up the buckle is a good thermal conductor. A thermal conductor is a material through which thermal energy flows easily. Atoms in good thermal conductors have electrons that move easily. These electrons transfer kinetic energy when they collide with other electrons and atoms. Metals are better thermal conductors than nonmetals. The cloth that makes up a safety belt is a good thermal insulator. A thermal insulator is a material through which thermal energy does not flow easily. The electrons in atoms of a good thermal insulator do not move easily. These materials do not transfer thermal energy easily because fewer collisions occur between electrons and atoms. Page 19, specific heat. The amount of thermal energy required to increase the temperature of 1 kilogram of a material by 1 degree Celsius is called specific heat. Every material has a specific heat. It does not take much energy to change the temperature of a material with a low specific heat, but it can take a lot of energy to change the temperature of a material with high specific heat. Thermal conductors such as the metal safety buckle in Figure 8 have a lower specific heat than thermal insulators such as the cloth safety belt. This means it takes less thermal energy to increase the buckle's temperature than it takes to increase the temperature of the cloth safety belt by the same amount. The specific heat of water is particularly high. It takes a large amount of energy to increase the temperature of water. The high specific heat of water has many beneficial effects. For example, much of your body is water. Water's high specific heat helps prevent your body from overheating. The high specific heat of water is one of the reasons why pools, lakes, and oceans stay cool in the summer. Water's high specific heat also makes it ideal for cooling machinery, such as car engines and rock-cutting saws. Figure 8. On a hot summer day, the air in the car is hot. The temperature of thermal conductors, such as the safety belt buckles, increases more quickly than the temperature of the thermal insulators, such as the seat material. So here's a belt buckle. Thermal insulators have high specific heat. Thermal insulator with a high specific heat. Thermal conductor with a low specific heat. Thermal conductor with a low specific heat. This is the seat. This is the buckle. And this is the controls, the gears. Page 19. Thermal expansion and contraction. What happens if you take an insulated balloon outside on a cold day? This is an insulated balloon. Thermal energy transfers from the particles that make up the air inside the balloon to the particles that make up the balloon material and then to the cold outside air. As the particles that make up the air in the balloon lose thermal energy, which includes kinetic energy, they slow down and get closer together. This causes the volume of the balloon to decrease. Thermal contraction is a decrease in a material's volume when its temperature decreases. Decrease means goes down. How could you reinflate the balloon? You could heat the air inside the balloon with a hairdryer, like in Figure 9. The particles that make up the hot air coming out of the hairdryer transfer thermal energy, which includes kinetic energy, to the particles that make up the air inside the balloon. As the average kinetic energy of the particles increases, the air temperature increases. Also, as the average kinetic energy of the particles increases, they speed up and spread out, increasing the volume of the air inside the balloon. Thermal expansion is an increase in a material's volume when its temperature increases. Thermal expansion and contraction are most noticeable in gases less noticeable in liquids, and least noticeable in solids. Hot air balloons. How do hot air balloons work? As shown in figure 11, a burner heats the air in the balloon, causing thermal expansion. The particles that make up the air inside the balloon move faster and faster. As the particles collide with one another, some are forced outside the balloon through the opening at the bottom. Now there are fewer particles in the balloon than in the same volume of air outside the balloon. The balloon is less dense and it begins to rise through denser outside air. To land the hot air balloon, the balloonist allows the air inside the balloon to gradually cool. The air undergoes thermal contraction. However, the balloon itself does not contract. Instead, denser air from outside the balloon fills the space inside. As the density of the balloon increases, it slowly descends. Descends means goes down. Oven-proof glass. If you put an ordinary drinking glass into a hot oven, the glass might break or shatter. However, an oven-proof glass dish does not damage in a hot oven. Why is this so? Different parts of ordinary glass expand at different rates when heated. This causes it to crack or shatter. Oven-proof glass is designed to expand less than ordinary glass when heated, which means it usually does not crack in the oven. Convection. When you heat a pan of water on the stove, the burner heats the pan by conduction. This process, shown in figure 12, involves the movement of thermal energy within a fluid. The particles that make up liquids and gases move around easily. As they move, they transfer thermal energy from one location to another. Convection is the transfer of thermal energy by the movement of particles from one part of a material to another. Convection only occurs in fluids, such as water, air, magma, and maple syrup. Density, thermal expansion, and contraction. In figure 12, the burner transfers thermal energy to the beaker, which transfers thermal energy to the water. Thermal expansion occurs in water nearest the bottom of the beaker. Heating increases the water's volume, making it less dense. At the same time, water molecules at the water surface transfer thermal energy to the air. This causes cooling and thermal contraction of the water on the surface. The denser water at the surface sinks to the bottom, forcing the less dense water upward. The cycle continues until all the water in the beaker is the same temperature. Figure 12. The cycle of cooler water sinking and forcing warmer water upward is an example of convection. 1. The burner heats the water. As the temperature of the water increases, its density decreases. The cooler, denser water sinks. This forces the warmer, less dense water upward. 3. Warm water forced to the surface loses some of its heat to the air. Therefore, the surface water becomes cooler and its density increases. When the surface water's density becomes greater than the water near the burner, it will sink and force the warmer, less dense water to the surface. Convection currents in Earth's atmosphere. The movement of fluids in a cycle because of convection is a convection current. Convection currents circulate the water in Earth's oceans and other bodies of water. They also circulate the air in a room and the materials in Earth's interior. Convection currents also move matter and thermal energy from inside the sun to its surface. On Earth, convection currents move air between the equator and latitudes near 30 degrees north and 30 degrees south. This plays an important role in Earth's climates, as shown in figure 13. Figure 13, currents in the atmosphere influence the locations of